Suppose we want to find the tangent line to this hyperbola, x squared minus y squared equals 1, at the point 2 comma square root of 3. So that's right here. Now, this graph isn't, on this graph, x isn't a function of y, and also y isn't a function of x, right? This graph doesn't pass the horizontal or the vertical line test. So since we can't get an explicit function like this, it's not totally clear how we would be able to find a derivative in this case, or a slope of a tangent line, right? This isn't going to be possible. Well, since we're interested only in this point 2 comma square root of 3, if we sort of zoom in on this point and throw away the rest of the graph, right? Well, near this point, this part of the graph does pass the horizontal line test, right? As long as we just throw away everything else. So on this part of the graph, y actually is a function of x, or x is a function of y, but let's stick to having y being a function of x. The problem is that we don't have an explicit formula for y as a function of x. Now, for this particular example, this is simple enough that actually with some work we could get an explicit formula, but trust me that in some situations it's basically impossible to get an explicit formula for y in terms of x if the equation that you start with is complicated enough. So in this kind of situation where we know that y is a function of x but we don't have a formula for it, how could we find the derivative of y, right? What we're really looking for is dy dx, but we can't find a formula for y as a function of x. Well, if y is a function of x, then what this equation actually says is x squared minus y of x squared equals 1. And both sides of this equation, they're both functions of x. The left is clearly a function of x because it has x's in it. The right is, well, it's a constant, but you know, a constant is a constant function, so it's also a function of x. And if these two functions of x are equal, then their derivatives are equal. So what we ought to be able to do in this situation is differentiate both sides. Right. If these two functions of x are equal, then their derivatives will be equal as well. And if we take the derivative on both sides, then dy dx is going to show up. And then maybe we can make some progress on solving for dy dx. So that's the idea here. If we start with an equation, we can treat y as a function of x implicitly. So we aren't explicitly solving for y, but we're implicitly treating y as a function of x. So when we do that, then we can take a derivative on both sides and hopefully find dy dx. So that's the idea for finding a derivative when you only have y implicitly as a function of x. For that reason, this technique gets called implicit differentiation. So let's use implicit differentiation to find the slope of this tangent line at 2 comma square root 3. So that was right here. All right, so we're going to take this equation and hit both sides with the derivative with respect to x, like this. Now, as we do this, we have to be really careful because this y right here, remember, we're treating it like a function of x. Even if it's not written that way, implicitly, it is a function of x. And so this y inside here is actually, it's inside of a squaring, right? So we have a square function, and inside of that is another function of x. So this is a composition. So we're going to have to be really careful about using the chain rule when we do this. So on the left-hand side, derivative of x squared, that's no problem. That's 2x, right? Derivative of x squared with respect to x is 2x minus. And now the derivative of y squared. So here's where we have to be careful. This has an inside and an outside. So the outside part is this squaring. So use the power rule for the derivative of the outside. 2 times the inside to the first. But the inside is y. Okay, and this is a first power. It's not a prime. Okay, now the chain rule says we have to multiply by the derivative of the stuff inside, which is y. And the derivative of y is dy dx. All right, and then on the right-hand side, derivative of 1, that's 0. All right, you can see that the derivative we wanted, dy dx, it showed up right here. So now we can just solve for it algebraically. So we can move the 2x over, I guess divide everything by 2 first. These 2's are gone. Move the x over, minus dy dx equals minus x. And that means dy dx is, I'm sorry, I lost a y here. Now we can cancel these minus signs, divide both sides by y. Dy dx is x over y. All right. So what we got here is a formula for dy dx, but it depends on both x and y. And that actually makes sense because the slope of the tangent line to this graph depends not just on the x-coordinate. You can see that because for this x-coordinate too, there are 2 different y-coordinates, right? 2 different points on the graph. So, and one of them has a positive slope and one has a negative slope. So you can't tell what slope you need just by knowing x on this graph. You have to know x and y. And that's why both x and y show up in this formula. So now that we have a formula for dy dx, we can use this point that we were thinking about, 2 comma square root of 3. So we can take dy dx and evaluate it at the point 2 comma square root of 3. So plug in our x value and our y value. So the slope of this line is 2 over root 3. So this process will work in general if you have an equation and you want to find an expression for dy dx, but you can't or don't want to solve explicitly for y. So let's look at one more example. The process is going to work the same. So when we have an equation, right, this particular equation, it looks like that. To find y prime, we'll differentiate both sides of the equation. And as we do this, we have to be really careful about the chain rule. So differentiating the left-hand side gives us 3x squared plus, now we have to do a product rule. So derivative of x is 1 times y squared plus x times the derivative of y squared, which is 2 times y prime. That's the chain rule. Okay, plus derivative of y squared. Well, again, this is the chain rule. That's 2y prime. And then on the right-hand side, derivative of 1 is 0. Okay, so if you want to use implicit differentiation to find y prime from an equation, differentiate both sides. Now solve both sides for y prime. You can see we have 2 terms with y prime. So let's keep those 2 terms on the left. Let's move the other 2 terms to the right. So this gives us 2xy prime plus 2y prime equals minus 3x squared plus minus y squared. Now on the left-hand side, both terms have a y prime, so we can factor out that y prime. 2xy plus 2y times y prime equals minus 3x squared minus y. And now we can divide both sides to get y prime by itself. So y prime is minus 3x squared minus y over 2xy plus 2y. All right. So first we differentiated both sides, and then we solved the resulting equation for y prime. Right? In general, how you'll do that is get all the terms without y prime to one side and all the terms with y prime to the other side, factor out the y prime and divide. That's usually how it will go. And then finally, if you have a particular point in mind on the original graph, then you can plug those coordinates into the expression that you got to get the slope of the tangent line at that point. So for example, for this particular example, the point 0, 1 is on this graph, so the slope of the tangent line at 0, 1, we just take our expression for y prime, but we plug in 0, 1. So plugging in 0, 1 into this, we get, let's see, in the numerator, just minus 1, so plus 1, over, let's see, 2 times 0 plus, let's see, 2 times minus 1, so we get minus a half. And yeah, it looks like the slope of the tangent line here is minus a half. That seems about right. Or another point on this graph, another nice easy point on this graph is 0, minus 1. So the slope at 0, minus 1 is y prime 0, minus 1. I did something wrong here. Oh, yes, okay. Sorry, I need to back up. This, I was supposed to be plugging in plus 1 here, so this should be a plus, but this should be a minus. So it still comes out to be minus a half, but the minus sign came from the numerator, not from the denominator. Okay. Now plugging in 0, minus 1, we get, in the numerator, we get a plus 1 this time, over still 0 plus 2 times minus 1, so we got minus a half. So I must have done something wrong here. Did we make a mistake? What happened? Okay, I found it. This y is supposed to be squared. So this should be squared, this should be squared, that should be squared, this should be squared. This parenthesis belongs here. So that's still minus 1/2. But, okay, now, right, we're plugging minus 1 into here. That gets squared. So now it's minus 1 over minus 2. So it's plus a half. There we go. And that looks right. Okay, so careful with your algebra, folks. But you can see that, again, like in our last example, this expression that you get from implicit differentiation, it can tell you the slope of the tangent line at any point on this curve. Right? You just have to plug in a point on the curve.